Hello friends, today I'll be giving a small presentation on the MergeSort algorithm. You must have heard several terms related to the MergeSort algorithm such as divide and conquer algorithm, stable or unstable sorting, comparison-based sorting algorithms, and yet some of these terms might sound quite confusing. Well, there's no need to worry at all. We'll be going over all of these terms in just a while. But first, let us start with the basics and see what an algorithm really is. An algorithm is a step by step instruction for solving some problem. Starting from an initial state, if we follow these instructions step by step correctly, then we will eventually produce an output and terminate at the final state. The transitions from one state to the other may not be deterministic, in which case the algorithm is called a randomized algorithm. Algorithms exist for a wide variety of problems. One such problem is that of sorting. Now let us dive deeper into sorting. Sorting refers to the arrangement of data in some logical order. The logical order may be anything that is defined by the user. Let us understand this with the help of an example. Suppose you are given currency notes of different denominations and you are asked to sort them in the increasing order of their denomination. In this case, the resulting order will be rupee 1 notes, followed by rupee 5 notes, followed by rupee 10 notes, followed by rupee 20 notes, and so on and so forth. It is worth noting that this is not the only possible logical order that these notes can be sorted in. You may as well sort them in the decreasing order of their denomination, or you may even sort them in the increasing order of the area of the currency notes. Hence, we conclude that there can be n number of logical orders that can be defined with respect to the data, and sorting can be done for any of them. Let us understand this with the help of another example. Any academic institution, such as IITD, has to have certain student records that contain the name, age, roll number or entry number, contact details, etc. regarding the students. These records have to be organized in some order or the other. Suppose that this institution chooses to organize them in the order of their roll number or entry number. This again is a classic example of sorting. Sorting algorithms can be distinguished on the basis of their complexity. For example, there are order n square sorting algorithms such as bubble sort, insertion sort, etc. Then, slightly better algorithms in terms of time are the order n log n algorithms, such as merge sort, that we'll be looking deep into in this presentation, quick sort, heap sort, are other such examples of order n log n sorting algorithms. Furthermore, there exist even order n algorithms for sorting, such as bucket sort, radix sort, etc. However, as we know, every algorithm has its own merits and demerits, and we'll be looking at the merits and demerits of merge sort with respect to other algorithms in a while. Next, sorting algorithms can also be classified on the basis of stability, whether or not they are stable, and whether or not they are in place algorithms as well. Now, what does a stable sorting algorithm mean? A sorting algorithm that does not change the relative order of equivalent items is called stable. Now, what does that mean? Let us take the following example. Say, you are given a list of animals and you are asked to sort them on the basis of their size. We know that an ant is the smallest of these animals, hence, it comes at the first position. Next in order come cat and dog. Now we realize that cow and buffalo are are approximately equal in size and are less than elephant. Hence, both these orders are valid sortings. However, we can distinguish between them on the following basis. In a stable sorting algorithm, cow will come before buffalo, since in the initial sorting algorithm provided to us, cow was before buffalo. Hence, the second list is a stable sorting. However, in the third list, the order of cow and buffalo is different from what it was in the original list provided to us. Hence, we define it to be an unstable sorting algorithm. Similar to this case, we can generalize the principle as follows. Whenever the relative order of equivalent terms is preserved in in the output list, then we call that algorithm as a stable sorting algorithm. If the property is violated, then we call it as an unstable sorting algorithm. Now let us look at what does an in-place sorting algorithm mean. A sorting algorithm that uses only a constant amount of extra space is called an in-place sorting algorithm. The intuition behind it is that it modifies the order of the elements within the list and does not use a more than constant amount of extra space to modify the elements. For example, quicksort is an in-place sorting algorithm. We will see that some variants of MergeSort are also in-place sorting algorithms. Now let us take an example of an in-place algorithm. Say you are given the problem of reversing elements in a list. Now, this task can be done both in place as well as not in place. Let us first look at the algorithm that does not do this task in place. If per se we are given the list of elements that we have to reverse and we initialize another list and of the same number of elements. Now, if at the ith position of the new list we assign the value that is at I distance from the end of the given list, then this will lead to a valid solution. However, note that in this case we have used an order n amount of extra space to solve this problem. Since we have initialized an array that is of an equal size as that of the given array. Let us have a look at an in-place algorithm that does the same thing. What if we could have exchanged elements that are at equal distance from the ends in the given array? This algorithm would have also reversed the list, however, without using more than constant amount of extra space. With this, let us move on to divide and conquer algorithms. Divide and conquer draws its analogy from war-based scenarios. Say, for instance, the goal is to conquer a country, which represents a very big problem. This goal of conquering an entire country can be broken down into several sub-problems. Say, the country has 8 provinces. Now, conquering the whole country can be looked at as conquering each of those 8 provinces. Hence, our smaller goal is to conquer each of the province. Once we have conquered each of the province, we in a way have conquered the entire country. So combining all these small goals, we have conquered the entire whole country. This is how divide and conquer algorithms work. They work by breaking a large problem into several sub-problems. Each of those sub-problems is then solved in order to solve the larger problem. In order to solve a divide and conquer algorithm, what is first necessary is to identify the base case. Once we've done that, we can move on to the divide step. The divide step involves dividing the problem into smaller tasks. Each of these tasks are known as the subproblem. Next, we need to conquer each of the subproblem. This is where identifying the base case actually helps. The subproblem needs to can be solved by reducing the solution to the base case, which in itself is the solution. Once all these subproblems are solved, we combine the solutions of the subproblems in order to get the solution to the larger problem. Now let us look at why is merge sort called a divide and conquer algorithm. In merge sort, in order to sort an array consisting of n elements, we first of all divide the array of n elements into two smaller arrays of n by 2 elements each. This is where we used the divide step of the divide and conquer algorithm. Next, we sort each of the smaller subarrays of n by 2 elements each. This is where we are solving the subproblems. On doing so, we will obtain two subarrays, two sorted subarrays of n by 2 elements each. The last step involves merging both the smaller subarrays to obtain a larger sorted subarray. In this way, merge sort is a divide and conquer algorithm. Now let us look at the intricate details of each of these steps involving merge sort. The first step is to identify the base case. The base case in case of merge sort is a list containing only a single element, because a list containing only a single element is in itself sorted. Hence, if the list length of the list is less than equal to 2, we return the list itself. Now let us look at each of the steps involved in the merge sort procedure. The first step, as we saw, is the identification of the base case. Remember that the base case is that subproblem which is in itself the solution. So we need to identify that array which in itself is sorted. An array consisting of only a single element is such an array. Hence, a singleton array is the base case of the merge sort procedure. As we can see, even in the pseudocode of the merge sort procedure, we have we have the clause saying if the length of the array is less than 2, then return the list itself. The next step that we need to look at is the divide and conquer procedure. Since the list is sorted when it contains only a single element, so we need to split the list into halves until we can no longer split it into halves. That is, when we have reached a list containing of only a singleton element. This is how this procedure will be carried out. Say for instance, we need to sort an array that has the following elements: 11, 28, 8, 15, 50, 20, and 90. We divide it into two subarrays. We recursively keep on dividing these arrays into subarrays until we reach arrays of size 1. At this point of time, notice that these subproblems are itself the solution. So from here on, we'll be moving on uh, to combine the solutions of these subproblems to generate solutions for larger problems. Now let us see, why does this work? Here we are actually dividing the problem into smaller problems. When we reach the base case, we have sorted lists. From there on, we can solve the smaller problems and then combine the small solutions to form the actual sorted large list. What we actually mean by combine is to combine the small sorted subarrays in the first and the second half to produce a final sorted array. Let us look at this step in greater detail. Formally, this is called the merge step, wherein our aim is to combine two smaller sorted lists in order to form one big sorted list. Say for instance, at some point of time in the merge sort procedure, we encounter the following two sorted sublists: 1, 4, 6, 8, 11, and 2, 3, 5, 7, 9, and 10. And our aim is to produce the following array: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Let us see as to how will we go from these two sorted smaller arrays to a large sorted array. The first step involves comparison of the first elements of each of those two subarrays using two pointers. Let us look at this in greater detail. What we actually mean by this step is we need to maintain two pointers pointing to the start of the two subarrays initially. Now we need to compare the starting elements of both these subarrays. Here, as is obvious, 1 is less than 2, so the starting element of the left subarray is smaller than the starting element of the right subarray, in which case we arrive at the second step of the merge sort procedure, which says add the smallest element to the final array and increment its pointer. Let us look at this step in action. Now, we are the final array that we'll be forming out of the combination of these subarrays now contains 1, and as you see, we have incremented the pointer in the first subarray by 1 since its first element has already been taken. The next step is to repeat each of these above steps till one of the subarray is empty. That is, the pointer of that subarray exceeds the length of the subarray. In this case, at, uh, at this point of time, we have to compare 2 with 4. Since 2 is less than 4, so at this step, 2 will be included in the final array and the pointer corresponding to the subarray 2 will be incremented like this. Since 3 is less than 4, we'll be including 3 into our final array as the next step. Notice at this point of time that two elements successively came into the final array from the same subarray. This is exactly the reason why choosing alternate elements from both the subarrays will not form the final sorted array in all the cases. Hence, it is a point to be noted. Next, we need to compare 4 with 5. Since 4 is less than 5, it will be included in our final array and its pointer is incremented. 5 is less than 6, so we'll include 5 as the next element and the pointer is incremented to 7. Since 6 is less than 7, 6 will be included in the next step. Since 7 is less than 8, 7 is included in the next step and its pointer is increased. Since 8 is less than 9, 8 is included in the next step and its pointer is increased. 9 is less than 11, hence it is included in the final array and its pointer is increased. 10 is less than 11, hence it is included in the final array and its pointer is increased. Whoa! Now that we have reached an interesting point in our merge sort procedure, let us look at it in greater depth. Here, one of the pointer has exceeded all the elements in a subarray. So, we have reached the end of the third step of our merge sort procedure. Let us look at what we need to do next. Next, we need to append the non-empty subarray to our final array. Here, as we see, subarray 2 is empty of any new elements, whereas subarray 1 still contains one element, in which case we will append this element to the end of our final array. This marks the end of our merge sort procedure, and as you can see, we have obtained a sorted list. Now let us look at what are comparison-based sorting procedures. If the final order is determined only by a comparison between the input elements, then such a sorting algorithm is called a comparison-based sorting algorithm. In the merge step of the merge sort procedure, we choose an element only from one of the two arrays after comparing the top elements of the two arrays. Hence, by definition of the comparison-based sorting algorithms, merge sort is a comparison-based sorting algorithm. Now, let us look at a complete example of the merge sort procedure so as to have clarity of every step in totality. Consider the following input to the merge sort procedure: 11, 28, 8, 15, 50, 20, and 90. We are given the task of sorting this array using the merge sort procedure. So, as the first step, we'll divide the given array into subarrays. At this step, we see that the subarrays are still not at the base case, so we further divide each of these subarrays. The same problem continues with 3 of the 4 subarrays obtained. However, one of the subarray that contains only the element 90 has already hit its base case, so we will no longer divide it. However, we shall still divide the rest of the subarrays. At this step, all of the subarrays are at their base cases, hence they themselves are sorted subarrays. With this, our divide step is over, and now we have to and we have conquered each of the subproblem. The only thing that is left now is the merge step. When we merge 11 and 28, uh, we we obtain a sorted subarray of two elements that consists of 11 and 28. Similarly, we obtain sorted subarrays in the other cases as well, that are 815 and 2050. Note that since 90 was not further divided, hence at this step it will not even be merged with anything else. However, it will be merged with the subarray consisting of 2050 in the next step. Using the merge procedure as described a few minutes ago, we will obtain the following subarrays that are larger than the subproblems that we just solved and are yet sorted. On merging these two subarrays, we will obtain our final answer, that is the sorted array 8, 11, 15, 20, 28, 50, and 90 in the order that we wanted. This marks the end of our example. This marks the end of our example, and I hope that this would have clarified the working of the merge sort procedure. Let us look at the pseudocode of the merge sort procedure. The merge sort procedure basically contains only two main functions. One is the merge sort that is actually called upon the unsorted array, and a helper function that is the merge function that it internally uses. Let us first look at the merge sort procedure. The merge sort procedure is given the unsorted array as well as the indices between which we need to sort it. So, only if the right index is greater than the left index do we need to sort it. Otherwise, the given array is not of positive length, hence we don't need to sort it any further. The first step involves calculating a middle index, that is the average of the left and the right index. Considering the divide and conquer step, we'll call the merge sort procedure recursively on the left sub half and the right sub half. After these two steps, our the array would have been sorted between the indices L to M and from M plus 1 to R. However, it is not sorted as a whole between L and R. So we need to perform the merge step and give it the parameters array L, M, and R. Now let us look at the integrate details of the merge procedure. The merge sort procedure, as we saw earlier, requires us to repeat the following statements till we reach the end of either one of the subarrays. Inside this loop, we first compare the initial elements of both of these sorted subarrays and copy the smaller element into a new array. Note that we need to initialize a new array that has size equal to the difference between L and R for the merge step. We will be using this information later on to calculate the space complexity of the merge sort procedure. So we need to copy the smaller element into the new array and increment the pointer of the subarray from which we took that element by 1. We will loop around this procedure till one of the subarray has no new elements left to be given to the new array. After this step, we will append all the elements of the non-empty subarray to the new array. Once we have done that, our new array contains all the elements between L and R in the sorted order. What is left is only to copy back the array back into the original array between the indices L and R. With this, the merge procedure is complete, and using the merge procedure, merge sort, the pseudocode of merge sort is also complete. Let us do the asymptotic analysis of the merge sort procedure. First of all, let us analyze the time complexity of the merge sort procedure. Let Tn denote the time taken to sort an array consisting of n elements. In the pseudocode of the merge sort procedure, we first of all recurse on the left subhalf and the right subhalf. Therefore, the divide and conquer step contributes 2Tn by 2 to the time complexity of the merge sort procedure. Once this is done, we call the merge procedure on the uh, on the indices to form the larger sorted array from the two subproblems solved. Note that the merge procedure goes over each element between L and R exactly once. Hence, it takes order n time, where n is the length of the array that is to be sorted. In totality, The total time taken by the merge sort procedure can be written down in the following recurrence relation. Tn is 2Tn by 2 plus theta of n. On solving this using the recursive tree method, we obtain Tn to be equal to theta n log n. Hence, the time complexity of merge sort procedure is order n is theta n log n. Note that this is significantly better than the n-square algorithms that we discussed during the beginning of the presentation. Next, we need to analyze the space complexity of the merge sort procedure. The only additional space is required in the merge step in different recursive levels. At any step, the maximum space required is equal to the length of the subarray that is to be merged. With this analogy, the largest amount of extra space will be required only when the two halves of the original problem are to be merged, in which case the additional space required will be equal to order n, where n is the length of the array that was initially given to us. Hence, the space complexity for merge sort procedure is also theta n. Now, the question that arises is whether or not merge sort is a stable procedure and an in-place procedure. It is now that we will address these two issues. Merge sort can be implemented as a stable algorithm if we choose the element of the left subarray when the first elements of both the subarrays are equal in comparison and add that element to the final array, then the resultant merge sort implementation will turn out to be stable. Next comes the in-place check. The implementation of the merge sort procedure described above is not in place. However, it is possible to implement merge sort as an in-place algorithm. Since the implementation of merge sort as an in-place algorithm is complex, we shall not be referring to it here. However, you can refer to the practical in-place merge sort by Nordic Journal of Computing 1996 for its details. Now let us look at a few more properties of merge sort. The implementation of merge sort that we saw above was not in place. Merge sort, as we implemented above, requires an auxiliary order n extra space, although there exists an in-place implementation of merge sort, for the details of which you can refer to the following journal. Merge sort is stable if we make sure that the left value is sent to the target on equal values. Furthermore, merge sort can be used in external sorting when the size of the input is too large to fit into memory. Now, the question arises, what is external sorting? If the size of the input is small enough such that the entire input can be read at the same time, then it is called an internal sorting. However, if the input is so large that it cannot be read at the same time, then it becomes the case of external sorting. Merge sort can be used for external sorting when the size of the input is too large to fit into memory. Merge sort is also used extensively in sorting linked lists in order n log n time and without using any auxiliary space. Note that in the merge step involving linked lists, we do not require any extra space. Hence, merge sort is really effective in sorting of linked lists. It is even better than other order n log n algorithms such as quicksort because quicksort requires a lot of random accesses that are quite costly in a linked list. However, merge sort procedure overcomes all these difficulties and proves out to be the best for sorting linked lists. Now, to describe the external merge sort in greater detail, what we actually do is we sort the chunks that fit into memory and then merge the sorted chunks together. The algorithm first chooses m elements at a time and writes back the sorted elements in the external memory. Here, m is the size of the main memory. Now, it recursively performs m by b way merge, where B elements from each sorted lists are brought into the main memory and their minimum is output. With this, we come to the end of our presentation. Thanks a lot for watching this video.